Hi guys, welcome to the ML with Python workshop series, workshop number 4. So this is a fourth one out of 6. So last week we have started off with the machine learning introduction, and we have done with linear regression model building session. And today we are going to have next algorithm, that is logistic regression. So we have a trainer for today is Mr. Surya Tej. He is from SmartBridge, which is a tech company of IBM. So Surya is a senior most trainer in SmartBridge company. So where he has got 5 to 6 years of experience only in handling this online boot camps and developing AI and ML sort of applications. So handing over session to Surya. Surya, please.
Yeah, thank you, Mr. Tej. Good afternoon to all the participants. So myself, Surya Tej, I work as a machine learning engineer. So today our topic is logistic regression. So before jumping into logistic regression, first we'll just have a small brush up on the topics which were covered previously. Okay. So with that previous topics, we'll just want to start our session, and after that, eventually we'll be starting with our logistic regression also. Just give me a minute. I'll be sharing the presentation. Yeah. So I think machine learning was already being discussed. Okay. So as I said, we're having a small recap of what was discussed. So as you all know, the definition is quite straightforward, and you are being learning it for quite a while. So it's a science of getting computers to learn without being explicitly programmed. Okay. So the thing is here, machines learn based on the data which is being given to it. Okay. And here we are having different types like supervised, unsupervised. So though you have already covered across supervised machine learning, where you have gone across linear regression, one of the supervised machine learning algorithms. So in supervised, as it is, the data is labeled. Okay. So based on the labeled data, algorithm is supervised and the model is being built. Okay. In the same way, when it comes to unsupervised, where the data is unlabeled, and we need to find patterns or kind of clusters, okay, based on the data which is being given to your algorithms. Okay. So before going to the actual building of model or anything like that, so first we'll see the traditional approach and the traditional programming approach, and your actual machine learning approach. So in general, in the traditional approach, suppose if you want to write a small program, okay, suppose to find out vehicle speed, whether it is going at high speed or normal speed or slow speed. Okay. If you take a small example to elaborate the differentiation between traditional programming and machine learning way of approach. In the traditional approach, you can see here, we need to write a program, and we have to give the data to that program. If you see here, a small kind of conditional statements were given, and as along with that, we are providing with some kind of data like speed. Okay. So with that speed, we are going to write some conditional statements. Based on that, we are going to achieve the output of whether it is overspeed or normal speed or slow speed. So that is a traditional way of programming where you used to do. But when it comes to the machine learning way of programming, here, as I've already mentioned, machine learning is data driven. Okay. So that means we have to fed the data, we have to train the model. Okay. Or train or build a model. Okay. So for training or building a model, what you have to provide data as well as output. When it comes to supervised learning, so we are, and is an example for supervised learning where you are providing with data. So when it comes to the same example here, the data is nothing but the speed is nothing but data. In both the instances, data is nothing but speed, and the output what we got are overspeed, normal speed, and slow speed. Scenario also, speed will be output will be overspeed, normal speed, or slow speed. Okay. The data will be something like, if you take the same example, 100 kilometers per hour overspeed, 50 kilometers per hour normal speed, 60 kilometers per hour normal speed. So like that, we have to fed the data in such a way that, okay, this is you're having a data of 100 kilometers per hour. For that, output is overspeed. 50 kilometers per hour, output is normal speed. 60 kilometers per hour, output is normal speed. 20 kilometers per hour, output is slow speed. In that way, we have to fed the algorithm with the data. Okay, data includes both input as well as output. Okay, so when you provide the data in such a way, algorithm will find the patterns between the inputs and the output. That pattern is nothing but your model. Okay, so model can also be called as a rule, or it can also be called, when it formed, is nothing but the insight which is being formed between the data and the output is nothing but your model. In such a way, your model will be built. The same approach here. The data is labeled here as we are talking about supervised learning, and vehicle speed is nothing but the data, and the output is nothing but our speed, normal speed, and this is nothing but rules. Rules are nothing but a model. Okay, so this is a traditional this is a difference between traditional approach and machine learning approach. I'm not saying that this kind of examples can be used as a machine learning problem statements. Kind of a small intuition to make you understand what is traditional approach and what is machine learning approach. Okay, so though we have gone across, you have already gone across linear regression. Logistic regression is somewhat connected to this linear regression. So that's the reason I just want to have a small quick recap on what linear regression is, so that we can eventually go to logistic regression. So coming to linear regression, as you have already gone across this, the main goal in this linear regression is to find out best fit line. So this linear regression is mainly on finding the line. Okay, so if you consider the equation of straight line, as you already known about it, y equal to mx plus c. Okay, so y is your, in terms of this algorithm, y is your dependent variable which you need to predict. Okay, and a naught is a constant, a1 is a coefficient of x, and x is your independent variable. Okay, so as we have already gone across this data set called salary versus experience. Okay, so you all know that salary is your independent variable, and the dependent variable is, salary is your dependent variable, and x, which is nothing but your independent variable, nothing but your experience. Okay, so based on the experience, we have to predict the salary of a person. Okay, in that scenario, what do you mean by a naught then? A naught is nothing but the base salary. Suppose if you take the context of the same salary and experience, a naught will be the base salary for every employee. Okay, which is constant. So suppose a person with a zero experience. Okay, zero experience is nothing but x is 0. Okay, when x is 0, obviously y equal to a naught. Salary will be a naught. That means the base salary of that particular company. Okay, so when x is equal to 0, y equal to a naught, which is nothing but the base salary, which is what you call base salary for total company. Okay, and a naught will be kind of same. Guys, suppose if you take this a general example, a 5 years experience guy is getting something around 1 lakh salary for suppose. Okay, same 5 years experience guy in other stream is getting something around 80,000. Okay, so that differentiation, that difference between the salaries is because of a1, which is nothing but kind of slope. Slope is nothing but it can be skill set, or it can be other activity, other skills. Okay, so that would be this a1. So we need to find this a1. Okay, obviously a naught will be obviously constant, so we need to find this a1 to get this salary predicted. Okay, that's what, so nothing but finding out the equation of line. So once we get the line is nothing but the prediction line for the given years of experience. So if you take the example of salary and experience, okay, so as I've already mentioned you, it is data driven. So we have to to build this model for this company, we have to fed data which is already been present for company. So this is nothing but the data which is already present. That means, so if you see here, so for 2 years I have experience, salary is something around some 30k. So for 4 years of experience, some 40K, something like that. So this is the already data which is being present with that company. Okay, so we need to build which generalizes this data. Whenever you give kind of an experience, our model should predict the salary for that experienced person. Okay, so to get that, we'll be building this kind of a line representation. We'll be getting this kind of a line. Now this line is just cannot be called as a best fit line. When it is called as a best fit line, the main goal in linear regression is to find out a best fit line. Okay, now with these points, with this x and y parameters, we will be getting an equation of line by finding out the slope. Okay, that line may not be the best fit line. Okay, so to get the best fit line, we need to minimize the cost function. So how to do that? Okay, so this is the best fit, this is the normal line which is being formed, but to get the best fit line, we have to minimize this. Okay, what are the line which you get with this data points? Okay, with that data points, whatever the line which is being formed, we have to adjust our model should algorithm should adjust the line in such a way that this y and y cap is minimum. Okay, so suppose if you see here y and y cap, these all, there is a difference, there is a difference, there is a difference. So we have to find out minimal difference between that y and y cap. So when that line is being adjusted with that minimal difference, that line we call it as the best fit line. So when the best fit line, what are the points which are there on that line will be the predictions for the respective experience. Okay, so you can see there, this is a cost function y and y cap. So we have to take the cost function for each and every data point to that line. Okay, and we have to do a summation squaring on it. The reason for doing the squaring is so there might be negative differences also. So for that reason, we are going to square it. So wherever this summation is minimum, the difference of the summation is minimum, that line we call it as best fit line. Okay, so it goes like this. Suppose this is the line which is being formed initially. For suppose it keeps on moving where it gets minimal number of cost function, minimal number of difference, summation of the difference. That line we call it as best fit line. Okay, so when we get this best, that line will be nothing but your prediction line. So what are the experience you're having? Suppose if you take this example here, so for 2 years of experience, what are the point which is there on this line? The respective y value is nothing but the predicted salary. That's what your linear is. The optimization to get this best fit line is done by an algorithm called gradient descent. So gradient descent is an optimization algorithm which helps us in achieving this best fit line in minimal number of iterations. So if you brute forcefully move the line in any directions, that time that may take a number of minutes or a number of hours. Okay, but to get that line with minimal number of iterations, okay, so this gradient descent will help us in getting our best fit line in minimal number of iterations. So this is just the recap what was discussed in linear regression. Okay, so now why it is interlinked to this logistic regression, that's what we're going to see. With that, we are going to start with the logistic regression. Hope all of you are able to understand what I'm saying.
Yes, sir. Yeah, please continue.
Yeah. So as we got to know that there are two types in your machine learning. One is supervised, another one is unsupervised. In general, broadly classified, there is also one more, which is a reinforcement. But the interest right now is on supervised learning. So in supervised learning, we are having two categories again. Okay, in that we are having regression, another one is classification. So regression, So how you're going to determine a data set need to be applied with regression algorithms, a data set need to be applied with classification type of algorithms. Okay, so regression in the sense, as I've said, in supervised learning, the output is or the model is supervised based on the output in the data set. Okay, so here to determine the type of supervised learning, we are going to identify it based on the output parameter. Output parameter is nothing but your dependent variable, nothing but, suppose in the previous scenario, salary parameter. Okay, so if the output variable is continuous in the sense, same previous scenario, if you have seen, the salary might be something like 2 lakhs, 1 lakh 50,000, 1 lakh 48,000, or 90 lakhs 40,000, 9 lakhs 40,000, or something like that. The output will be continuous. So whenever the output is continuous, then we are going to apply regression type of algorithms. When the output is categorical, so what is categorical or discrete? Categorical or discrete in the sense, whenever if you see your output column, the output column will be a fixed value. That means, suppose if you take example of kind of weather prediction, okay, so they take that output as whether it is going to rain or not. So in the output prediction, the output will be whether it is going to rain or not, yes or no. Only two categories will be repeated throughout your output column. Okay, so that's why the output is, if the output is discrete, then we're going to apply classification type of algorithms. So one of the algorithms in classification is logistic regression. So you're saying that it is a classification, and how come the word logistic regression? Okay, so by the end of the session, you'll be getting to know why it is called a regression. Okay, the point which you have to remember is that, so if the output is discrete or fixed or categorical, then we are going to apply classification algorithms. Okay, hope the point is clear with this classification, when to apply classification algorithms. So one more example for that is diabetic prediction, whether it's going to get diabetics or not, yes or no. Okay, two categories. It's not only two categories, can have three categories. Okay, high, low, medium. Okay, something like that, whether it's going to rain or sunny or kind of dry or something like that. So three categories, four categories, five categories. If you see in your output column, the output will be fixed with those five categories or six categories. So if the output is fixed in that output column, then we are going to apply classification type of algorithms. So one of the algorithms in that is logistic regression. So one of the important point is, remember, logistic regression is only used if there are only two categories in your output column. That means if you're having only yes or no, true or false, high or low, okay, 0 or 1. So logistic regression is capable of handling only binary classification data sets. Binary classification in the sense, as I've already mentioned, the output will be 0 or 1, high or low, good or bad, something like that. Only two categories will be present. Okay, so that would be, so binary classification is only used for logistic regression. Okay, I can also put it in other words, logistic regression can handle only binary type of data sets. Okay, there are other algorithms also coming forward where more than two categories or multiple categories can also be handled. Okay, so as of now, logistic regression only handles binary type of data sets. Okay, so now we're going to see how this binary classification works. Sorry, I mean how logistic regression works. As I've said, it is being derived from this linear regression itself. So we'll be using that linear regression which was discussed. So what we have done in your linear regression, we have drawn a best fit line, okay, based on the independent and dependent variables, so which is nothing but your experience and salary respectively. So we are going to predict the salary of the person based on the experience. Okay, so we have drawn some kind of a best fit line like this. Okay, so where we got minimal cost function when you do the summation between y and y cap. So this, suppose, is the best fit line which is being formed. Okay. Now consider same scenario. Just a minute. Yeah. So when you consider this scenarios, the same scenario, when it comes to classification, how your linear regression works. See, these points are nothing. I hope these points are clear. This thing is clear. This diagrammatical representation. So this is the experience. Suppose 2 years of experience. The data which is already been present is something like 30,000 of salary. 44 years of experience, 50,000 of salary, something like that. Okay. Now, based on output is our salary. Okay. So we are easily able to plot the points, points here. Okay. Now, when it comes to this scenario of logistic regression, where your output there are only two outputs, whether it is 0 or 1. So how are you going to draw the best fit line? If you take this same data set of 0 and 1 as outputs, okay, how your linear regression would do? That's what you're going to see here now. Okay, so with that, we're going to deriving it to our logistic regression. Suppose with the same thing, we are having a similar data set. Based on age, we have to predict whether a person is going to purchase a kind of a motorcycle or not. Okay, just an example sake, based on the age of the person, we are going to predict whether a person is going to purchase an item or not. Okay, so yes or no, only there are only two categories here. Here we are having multiple values because multiple positions, because our salary is a continuous value. Here our purchased column is, you'll be having either 0 or 1. 0 represents we will not purchase, 1 represents we might purchase. Okay, so if you plot the graph between age and purchase, okay, so age column will be having age x-axis, which is having age, will be having some points like 25 years, 15 years, 16 years, 17, 18, 20, 25, 30, 35, 40, 45, 52, something like that. The age column will be general age. Okay, and the purchase column will be either 0 or 1 because it is a classification data set. Okay, so when you plot the points, suppose for 15 years of experience, 15 years of age, okay, so he may not buy. For 20 years he may buy. 23 years he is not buying. 24 years he is buying. See, this data is already present. Okay, previous data. Okay, so when you plot the graph, the points will be plotted in such a way. You'll be having either 0 or 1. As I've said, 15 years he will not purchase. 16 he'll not purchase. 17 he will purchase. 18 he will not purchase. 19 he will purchase. Something like that. Just for this example sake. Okay, so here we are having two categories, 0 and 1, and we have plotted the points based on the output column. Now for suppose, though it is not an apted one, for suppose if you try to draw a best fit line, if you try to fix a best fit line between the points which are there here. Okay, so when you draw a best fit line like this, okay, just consider even after applying gradient descent, and the gradient descent has no option but to finalize this as the best fit line. Okay, so this is the best fit line for suppose according to the algorithm. This is the best fit line according to your linear regression algorithm. This is the best fit line which is being formed. The final or minimal minimal cost function line. Okay, so this is the line which is being formed. Okay, now what can you say about these points? What can you say about these points which are there on the line? See, our main interest would be 0, or outputs will be 0 or 1. Okay, the output which you're going to predict out of logistic regression will be 0 or 1. Okay, putting that aside, okay, so when you draw this, when you get a best fit line like this, okay, so when you see here these points which are there, the points which are there on this line are going beyond the output which should be there. Okay, the output should be either 0 or 1, but this is a line which is being going beyond that. And here you can also see here below, the output line is going below this one, below the actual age 0 line. Okay, So what can you say, what can you comment on these lines? Yeah, what can you comment on these lines on the charts, guys? You can see here you're having the lines. This is the line which is being drawn. Okay, just consider a scenario here. What can you comment about the points which are there on this line? Anyone on the chats? What can you comment about this line, the points which are there on the line? It is going beyond one. Okay, what can you interpret from that? Anyone? Okay, so you can see here these points, these the portion which are there here. Yeah, obviously this is not best fit. Obviously it is not a best fit line. Okay, but it is going, yeah, it is going beyond this. Okay, so when it is going beyond this, we can come into a conclusion that these people, so for suppose according to the algorithm, these people are having high probability, more or extremely extremely into buying this thing. We can also comment like that, right? Because it is going beyond one. Okay, they're extremely uh, uh, confident that they will be buying this. Okay, you can see these points, they're extremely not not good. Okay, can we interpret like that? Because you can see here, these are the baselines. 0 is one baseline, 1 is one baseline. Okay, so the points which are there on this line, they're going beyond that one. Okay, that means they're very much in a position, they're very much interested to buy that product. These age people who, according to the algorithm, these people are very much interested to buy the product, and these people are very least interested to buy that product. Okay, so either it is very much interested or very least interested. There are only two categories, either 0 or 1. So obviously, what can we conclude, these guys? What can we conclude about this? Can we give it to 1 or 0? These points which are there in the on top of this one, can we conclude it to 1 or conclude it to 0? On the chats, obviously 1, because they are going beyond 1, and these people are going beyond 0. According to our laws, according to our algorithm, we can just confine it to either these belongs to 1 category, these belongs to 0 category, because we're having only 2 categories, either 0 or 1. Okay, the same thing happens here. Okay, we'll be concluding them as 0 and 1. Okay, so then now the extreme parts are done. What about this, the part which is there in the exactly in the middle of that line? What about this? How can you conclude this line? Suppose a point is there here. Suppose one of the point is there here. Okay, what can you say, whether he's going to purchase that item or not? Suppose you're having a point somewhere here, whether he's going to purchase the item or not. On the chats, suppose here you're having, yeah, that's what we cannot analyze multiple outputs. Okay, I mean to say categorical values. We can only classify only binary outputs. Okay, suppose if you take here the point which is there, suppose if you take this point is going beyond half of, that is nothing but 0.5 line. Okay, so if it is going beyond 0.5, if it is greater, we can just conclude that if the points which are lying here, since it is going beyond 0.5, we can just conclude that as it comes to one category. If it is going below 0.5 or less than or equal to 0.5, you can conclude that as 0 category. Okay, so if the values are going beyond 0.5, we'll be concluding it as 1. We will be concluding the prediction as 1. If below 0.5 or less than or equal to 0.5, we can just conclude it as 0. Okay, so when you draw a best fit line according to linear regression, okay, so when this line is being formed, we will be converting that, we will be smoothing this curve. Okay, and we'll be confining it to either it belongs to 0 or 1 category. So in this medium, in the line which is there, the points which are there between 0 and 1, if the points are greater than 0.5, we'll be considering it as 1. If it is less than or equal to 0.5, we'll be considering it as 0. Okay. So here, how you will be getting the smoothened curve here. Okay. Then comes a picture of a sigmoid function. Okay. So when you apply sigmoid function on your linear regression, we will be getting this logistic regression equation. You can just take a note of it. When you apply when you apply sigmoid function on this linear regression, we'll be getting logistic regression equation. So sigmoid function helps you in finding that smoothened curves. Okay. So one more point here, when it comes to sigmoid function, the range of sigmoid function is from 0 to 1. Okay, the range is from 0 to 1. Okay. This can be there between 0 and 1. Just tell me, guys, how many will be present between 0 and 1 on the charts? How many values will be present between 0 and 1? Infinite, right? Now, what is continuous? Nothing but any value can be present. Okay. Here also, infinite values are there between 0 and 1. But we are keeping a kind of a threshold stating that if it is greater than 0.5, we'll just consider it as one category. Less than or equal to 0.5, we'll just consider it as 0 category. Okay. That's why the term says logistic regression. Why it is called regression? Because we can have infinite number of values, infinite number of continuous values between 0 and 1 itself. That's why the word regression comes into picture. Okay. We'll be threshold sigmoid function, logistic regression will threshold, I mean, when you apply the threshold of greater than 0.5 or less than or equal 0.5, we can come into conclusion that whether it comes to 0 category or 1 category. Okay. So you can just apply, people who are good in mathematics, they can just apply this y, substitute this y in this equation of sigmoid function, apply ln on both sides, we will be getting this kind of logistic regression equation. Okay. So that's how your logistic regression equation will be formed. So the curve which will be formed, hope all of you have taken this, the curve will be like this. Okay. The smooths are formed because of your logistic, because of your sigmoid function. Okay. So greater than 0.5, we'll be considering it as 1, less than 0.5, we'll be considering it as 0. Okay. So that's what happens with logistic regression. So that's what the interconnection. So since we apply sigmoid function on your linear regression equation, we'll be getting logistic regression, which is nothing but this kind of curve. Okay. So why it is called regression? Because you're having infinite number of values, 0 and 1. Okay, nothing but continuous values, but there is a boundary of 0 and 1. Okay, but the values are continuous. That's the reason you'll be having the word says regression. Okay, if it is greater than 0.5, we'll be considering it as 1. Less than or equal to 0.5, we'll be considering it as 0. Okay, so now we'll just start with the implementation of it, how this logistic regression can be built. Okay, so in between also we'll be coming across one of the going to evaluate your model. Okay, so we'll see some of the evaluation metrics for this logistic regression or any classification data set or any classification, I mean any class. So with that, we are going to evaluate your model. Okay, so we're going to start with the model building. So I'll be just opening my Jupyter notebook to show you the implementation of this how this logistic regression can be done, can be applied to your data set. Just a minute. Okay, audible. Okay, sure. Just a minute. This. Yeah. Just increase the screen size also. So I'll just open a new Python file. Okay. So I'll just give the name as a logistic regression. Okay. So now so I'll be just downloading the data set. Is it clear now? Is my voice audible? Is my voice clearer? Yeah, thank you. So I'll be just downloading the data set from this link, tinyurl.com/data-lor. Okay, just copy it. So I'm having the link. Okay, yeah. So this is the data set which we're going to use for the demonstration of logistic regression. Okay, the data set. Yeah, the most thing while building this logistic regression, obviously you have already gone across a linear regression. So first we are going to import the libraries which are or packages which are required for your building your model. So obviously import numpy as np, import pandas as pd, lt. So these are the packages which you're going to use for building your model. So use for graphical computations and pandas for loading your data sets and doing the pre-processing on the data set, and as well as matplotlib for okay. So first we are going to import the packages. Okay, so once the package is being loaded, so we're going to load the data set. We read underscore csv of. So we'll see the data set from here first. Okay, so this. So since I'm having it in the same folder of I'm just loading it directly. So I can see this is my data set. Okay, so this data set is nothing but somewhat similar to the problem which we have, the demonstration which we have seen previously. So here we are having total 5 parameters: user ID, gender, age, estimated salary, and purchased. Okay, so here you can see we have to predict whether a person is going to purchase some X item or not, based on age, gender, and estimated salary. And you can see here user ID, you're having some one of the columns called user ID. So this user ID is nothing but some kind of an ID column which will not be used for predicting whether we are going to purchase an item or not. Okay, so it is quite obvious we can just remove this user ID, because it doesn't help us in predicting whether a person is going to purchase an item or not. Okay, so first step which you are going to do is so we're going to remove that column, or we can also remove it while building your model. So when you are going to apply finally on your algorithm, we can also remove it. Okay, so at that time we'll just remove that ID column. Okay, as of now, the first and foremost thing which you have to do is you have to find whether there are any null values or not. Okay, so checking for null values. So the reason for going for checking null values initially in the initial stages is that, so if you want to do any operations, so if you're having any null values, the packages or the package which are there will not allow you to perform those operations, as there is some kind of data missing in your data set. Okay, that's the reason first we have to check whether there are any null values or not. So data set dot is null dot any. Okay, so dataset dot is null dot any will give you whether there are any null values or not. So you can see here there are no null values. We can also, suppose if you're having n number of columns, okay, instead of checking it whether there is false for each and every column, we can also apply one more simple fix here, that is null dot any. This will give you in the total data set if there are any null values or not. This also the same thing, this is also the same thing, but here if there are any null values, then you will be getting true here. If there are no null values, then we will be getting false. Okay, if you got true, then we can just go and check where you are having null values. So from the data set, it is quite from this step, it is quite clear that there are no null values. Okay, so we can just proceed to the next step. Since we are not having any null values, so we'll just go and drop our user ID column, because we are going to we are not going to use that user ID column. Okay, so df equal to, I'll just store it in one more variable called df. So data set dot, we can use a method called drop. So drop of, so here for the drop, if you want to see the parameters which can be passed in the drop method, use shift tab. So here we have to provide the label and the access. Okay, so label is nothing but which column you're going to drop. So I'm going to drop user ID column. So I'll just give it as same, it has to be case sensitive. And since it is a column which you're going to drop, axis for the column is 1. Okay, so for if you want to row, then the axis is 0. Okay, if you want to draw be 1. Now just print df. Is this visible to all of you?
A notebook I can see, Surya.
df and all things, right?
Yeah. User ID access one we can see.
Okay, fine. So if you just print the data set here, after removing that user ID column, so you can see here that user ID column moved. Okay, now so obviously before building any model, okay, before building any model, we need to perform these pre-processing steps. As these pre-processing steps were already being discussed, so I'm just going it directly on the flow. So you can see here we have just dropped one of the columns, and one of the important steps while pre-processing your data is that categorical columns. What are the columns you are having in the set? Any one of you on the chats? What are the categorical columns you are having in this data set? Anyone on the chats? What are the categorical columns you are having? Okay, purchased and categorical columns. See, categorical columns in the sense where you're having a fixed values. So you can see gender is one of the cat. So we'll be converting our categorical columns into numericals. The reason for that doing that step is that most of our algorithms which are there in the scikit-learn will not be in a position to handle categorical values. Okay, so that's the reason we are going to apply kind of one of the encoding techniques to convert the numerical columns into categorical columns into numerical columns. Okay, so for next thing is converting into numerical columns, converting the categorical column into column. Okay, so df, first we have to know how many categories are there. Okay, so df of gender dot values underscore counts. This will give you how many categories are there. No, age is not a categorical column. So df dot gender dot values underscore counts. This will give you how many categories are there and how many times those categories are repeated in that particular column. Okay, this step will give you that. So df dot gender dot value underscore counts. You can see here there are only two categories. One is male and female, and there are 204 categories of 204 records of a female, 196 records of male. Okay, so we'll go and perform this converting into numerical columns. So for that I'm going to use label encoder. See, there are a number of techniques for converting this categorical column into numerical columns. Some might use a replace, some might use one hot encoding, some might use label encoding. Okay, so here I'm going to use label encoding. So from sklearn dot pre-processing import label encoder. Okay, so I'm going to use label encode for converting into numerical columns. So first I'm going to create an object for this. L be equal to label encoder. Okay, people who are facing a problem, so just check it here once. Just a second. Just a minute. Okay. Yeah. Excuse me. So I'm going to create an object for this label encoder. Okay. Now for this label encoder we have to provide the exact location of your exact column of the gender. Okay, where you're having the gender, that column need to be provided. And one of the constraints for label encoder is that label encoder should be given with only one dimension one dimension arrays. Okay, or one dimension number arrays or series to it. Okay, So we are going to give it this label encoder our gender column. So to represent our gender column, we are going to use iloc. So I'm going to use in iloc. Iloc is nothing but index location. So df dot iloc. So if you want to represent, if you want to take gender column, I'm going to use df dot iloc of. Sorry, iloc of colon comma 0. Okay. So if you see here, if you just check it once, so you can see this is the gender column. Okay. So iloc will be used to reference. I'm going to reference this gender column. Okay, using iloc. So this I'm going to apply it on my label encoder. Okay, so what are the changes which going to be occurred, that should be replaced again into this iloc itself, into this gender itself. That's the reason lb dot fit underscore transform of. So we have to give the same thing. Okay, so when you perform this, now if you press df, so you can see here your label encoder has converted gender column into zeros and ones. Okay, so male is given as 1, gender is given as 0. So how label encoder works, initially it will just sort out in the form of alphabetical order. Okay, whenever it finds a new category, it will assign a number to it starting from 0. Okay, so since gender, okay, so here we had the first category, you can see here we had it as male. Okay, so we got that as male is being given as 1 and female is given as 0. Okay, so once the pre-processing of that is done, okay, so one of the steps which can be included is removing of outliers. If there are any outliers in your data set, outliers are nothing but data points which are moving away from your actual actual data set. Okay, the points which are actually moving away from your actual set are called outliers. So of outliers would be something like if you're doing any kind of salary prediction, for suppose, okay, suppose you're doing Amazon salary prediction. In the data set, we cannot use Jeff Bezos' salary for the salary prediction, because Jeff Bezos' salary is beyond the actual employee's salary. So actual employee's salary set. Okay, so Jeff Bezos' employee salary is nothing but an outlier. Okay, so as this to our instance as of now. Okay, so I'm going to remove the outlier using Z score. Okay, so I'm going to use a package called SciPy initially to calculate a Z score. So from SciPy, import stats. So you can just keep it as a heading here. Find outliers and removing it. So Z score, one of the methods is Z score. Just using it. Okay. So according to Z score, what are the, so we are going to calculate Z score for each and every data point which is there in your data. Okay, respect to the column. So if that Z score is going beyond -3 or +3 for any one of the data points, then that point is considered to be an outlier. I'm repeating it one more time. According to Z score, according to industrial standards, if the Z score value of any one of the any one of point in the data set is going beyond -3 or +3, okay, if the Z score value is going beyond -3 or +3, that value is considered to be as an outlier. Okay, so first we are going to find out the Z score. We are going to check whether it is going beyond -3 or +3. Okay, so I'm going to calculate Z score now. Z equal to np dot, tell you what this states, np dot absolute value of stats dot Z score. of DF. Okay, so these are all the z-score values of the respective data points which are there in your data set. Okay, so here, as I've said, plus 3 or minus 3, right? If it is going beyond minus 3 or plus 3, then we are going to consider as an outlier. Okay, so what we can do here is print the z-score values. So here we have to check it whether we're going to check across each and every data point whether it is going beyond minus 3 or plus 3. If it is going beyond minus 3 or plus 3, then we're going to consider it as an outlier. Okay, now in this scenario, since absolute numpy dot absolute, this will convert all the values which are there in this to positive values. So one of the small logic here is to check whether a value is going beyond minus 3 or plus 3. We can just convert all the values into positive values, and we can just check with only one condition stating that if it is going greater than 3 or not. Okay, instead of using multiple conditions for checking whether it is going beyond minus 3 or plus 3, we can just use whether it is we can just convert all the values into positive values. Okay, and just check with only one condition if it is going beyond minus 3 plus 3 or not. Okay, so these are the respective z-score values of our data set. Okay, now I'm going to check whether it is going beyond the 3 or not. Okay, so I'm going to define the threshold. So threshold nothing but your score, what value it should not exceed 3, right? So that's what our threshold here is. So I'm going to use a function called a method called np.where z greater than threshold. Okay, so this will give you whether if there is any value 3 or not. So you can see here it's quite obvious, it's quite clear that there is no value which is going beyond 3. That clearly states that there are no outliers in our data set. Okay. So if there are any outliers, then you might be getting some kind of values here, okay, in that array. So since it is not, the values are not going beyond 3, okay, so there are no outliers in our data. Okay, from here, from the above, we can just conclude that no outliers in our data set. Okay, so this is one of the pre-processing steps. There are no outliers in our, yeah. If there are any outliers, yes, obviously we have to remove that respective what do you call respective rows. Okay, if there are any outliers, then we have to remove it. Okay, so since we got to know there are no outliers, now we are going to go and split our data set into independent and dependent variables. Now just tell me guys, what are our independent variables in our data set? I'll just print our data set. So these are data set, right? What are the independent variables? Yeah, obviously that's what, since Giridhar, since it might affect our data itself. See, if you're having an outlier, that might increase your average, or you can just call it as mean. Okay, so that's the reason we are removing that part of our data. Okay, that's the reason for removing it, is since it is not valid for our building our model. Okay, so you can see what are the independent variables in our data set, guys? Yeah, gender, age, and estimated salary are independent variables. Very good. Okay, so I can just call it as features. So I'm going to store our independent variables in x. Okay, x is equal to df dot. I'm going to colon comma 0 colon comma colon 0 to 3. Okay, so this says that, as the syntax is quite clear, I guess. So this colon represents rows, this colon represents columns. I want all, if it is empty, I want all the rows, and I want a column starting from 0 to 3. 3 will not be considered, just like your array indexing, 3 will not be considered. And I'm going to convert it parallel into numpy arrays. To convert a pandas data frame into numpy arrays, I'm going to use dot value. Okay, so dot values will convert your data frame into numpy array. I'll just print x. So you can see here it is being converted into numpy array. Similarly, I'm going to store independent variable y equal to df dot ilog. Obviously, the independent variable is purchase. Yeah. So df dot ilog of colon comma -1 dot values. Print. Okay. So these are all your but per column. Okay. Now we got our x and y. Okay. So you can see here there is also one more pre-processing step to be done. Okay. So you can see here you're having x and y. Now if you see the points which are there between your x and which are there in the x. Okay. There's a large difference between your data points here. You can see 119, 19,000, 135, 2,000, 20,000 like that. So there is a large variation. Okay, so even though one of the important steps while building your model is standard scaling them or normalizing the values. Okay, so we are going to do one of the important steps, which is normalizing. Okay, I'm going to apply the normalization. Okay, so one of the scenarios where we can apply normalization is if there is large variation between your independent variables, then one of the best approaches is to perform normalization. Okay, and one more scenarios where we have to do a normalization is if there are any algorithms which are related to distance. If the algorithm consists of some kind of distance related calculations in their algorithm, in those scenarios also the normalization is one of the important factors. Okay, so here we are going to perform the normalization. So one of the normalization techniques is standard scaling. So I'm going to apply standard scaling here. So normalization is nothing but bringing all the values into one particular scale. Okay, so I'm going to standard scale the values. So first I'm going to import the package. No, it's not only for classification. You can apply normalization for all the algorithms. Okay, but it is compulsory to the algorithms where you're having a distance related thing in their algorithms. Okay, if the algorithm is based on a distance, then we have to for sure perform normalization. Okay, is also best practice to perform normalization. So from sklearn dot pre-processing import standard scalar. Okay, check the spelling. Excuse me. So I've just imported the package of standard scaling. Okay, I'll just create an object. S is equal to standard scalar. Okay, I'm going to perform standard scaling on my independent variables. So I'm going to store it back in X itself. So X is equal to sc dot so fit transform. Transform of X. So print X. So you can see these are all the standard scaled values. Okay, so actually the values actual meaning may not change. Okay, they will be brought into one single scale. Okay, that is nothing but normalization. So we have performed a normalization here, or nothing but standard scaling. Okay, now we are going to one more step here is the next step of since all the pre-processing steps are done, we are going to perform train test splits. Okay, as you have already gone across this train test splits, why we are going to split your data into train and test. Okay, the reason for that is, so once your model is built, okay, how you going to test your model, how you going to evaluate your model. Okay, for that you require some kind of test data with known inputs. Okay, so that's what we're going to do here. We're going to split our data set into train and test, and we're going to check whether we're going to use that test data for testing your model. Okay, so I'm going to use from sklearn dot model underscore selection import train test split. Okay, let's import the package of train test split. Okay, so train test split of, so here train test split, if you want to see the parameters which can be passed, use shift tab, place the cursor here and use shift tab. In general, we have to provide x and y parameters. Okay, your independent and dependent variables need to be passed in your train test split. So our independent variables are present in x, our dependent variables are present in y, x comma y comma test underscore size is equal to 0.2. So test size is nothing but how much data you're going to accommodate for testing, allocate for testing. Okay, so I'm going to use 0.2 represents 20% of data. So I'm going to use 20% of the data for testing, and I'm going to use 80% of my data set for training. Okay, so here that's what test size represents, 0.2, and it's not a fixed value depending on your data set. Okay, in general the standard value is 0.2. We can also use 0.3. 0.3 is nothing but 30% of the data. Okay, so but in general 0.2 would be considered, because if you take lot of data, allocate huge amount of data for the testing itself, it would be insufficient for your model to train. The training data will be insufficient. That's the reason I'm going to use test size as something around 0.2. Okay, and random underscore state is one more parameter called random underscore state equal to, so you can give any number here. In general 0 is going to be given. Okay, random underscore state is nothing but, now as I've said, 80-20, right? 80% for training and 20% for testing. Okay, now which 80% need to be taken? Is it first 80 records or last 80 records or middle 80 records? Okay, so when you use random state equal to 0, there is a small algorithm run behind it which picks 80% for training, some random 80% for training, some random 20% for testing. Okay, but the common thing here is if you use a 0, the same data would, if I'm using 0, if you are also using the same 0, the same 80 records which I got selected for training, the same 80 records will also be selected for you for testing. Okay, yeah. What happens if you took only 0.1 for testing? See, if you use only 0.1 of testing data, then while you're evaluating your model, you may not be getting correct conclusions to your model, whether it is a good model or not. That's the reason it should not be more, it should not be less. Something around 0.2 would be considered. Okay, so random state will help you in picking up the 80-20 sets. Okay, now the return values which are there written for these train test split function is that we are having 4 values coming out of it: x underscore train in the same order, x underscore train comma x underscore test comma y underscore train comma y underscore test. Excuse me. X underscore train comma x underscore test, y underscore train comma y underscore test. Okay, so this x train and x test are just variables, guys. Okay, these are variables. Okay, these variables can be any names. Okay, you all know that. So variables can be any names. Okay, but the order should be same. Here the first parameter will be the training 80% data. This will be training independent variable. See, when I say data set, you'll be having independent as well as dependent variables. Okay, these will be training independent variables, these will be testing independent variables, these will be training dependent variables of this data, testing dependent variables for this data. Okay, so these are inputs, these are outputs. For these inputs, these are outputs. Okay, so we got four sets coming out of it, 4 arrays. Okay, so if you want to check the shape also, see here, first of all just check the shape of x dot shape. So there are total 400 records and 3 columns. Now if you see here, what is the 80% of 400 records? Anyone? What is 80% of 400 records? If you want, you can just use this xtrain dot shape. Is it 320 or not? 80%. Okay, that's what 80% of the data is being given to train. And if you want to check with x underscore test dot shape, so that's 20%. So you can see here combinedly we'll be getting 400 records. See, these are inputs, that's why you're having how many independent variables you're having? 3 independent variables. So for the respective 320 records, the respective outputs are y underscore train dot shape. Just check it here. You can see here for this 320 records, these are the 320 outputs, respective 320 outputs, not any outputs, their respective 320 outputs. That means for these 320 records, 320 independent variables, these are 320 dependent variables. The same way, y underscore test dot shape, respective 80 records, respective 80 outputs. Okay, hope it is clear with the train and test. Okay, so once we perform the train and test, the next step is applying data on the algorithms. See, one important point here, most of the people get confused, is that we will not be building algorithms. In machine learning, we will not build algorithms, we will be building models. Okay, model is nothing but the pattern which is being formed, which is being recognized by your algorithm, is nothing but a model. Okay, so now we are going to perform your logistic regression. So first we have to load the data set, load your algorithm. So obviously all your algorithms, most of your algorithms are present in scikit-learn. So sklearn dot linear underscore model import logistic regression. Okay, logistic regression from sklearn dot linear underscore model import logistic regression. Okay, just import the package lr. I'm going to create an object lr dot logistic regression of. So I'm going to create an object. So this object can be anything, guys. Okay, so I've just given an object lr dot fit. So if you want to apply your data to your algorithm, you're going to use fit method. lr dot fit of. Here the important point which I have to remember, what we won't give x and y directly. Okay, we will be giving train data which is present in x train and y train. Okay, so this is the input x train comma y train. Okay, so since we have to provide the model with train data itself, lr dot fit of x underscore train comma y underscore train. Okay, so your model is built. See guys, you might think, sir, how this much fast? Okay, you can see there are only 400 records. Okay, so if you're having a huge data set of something around 10 lakhs or something like that, it would take some time. Since you are having a smaller data set, these are your model is built. Okay, you might be thinking, sir, what are all these parameters? Okay, so these parameters we call it as hyper tuning parameters. Hyper tuning parameters. Okay, so these parameters will be used if you want to tweak your model. or if you want to do any modifications to your algorithm, okay, internally, we can just pass on the parameters in this class. Okay, here as of now we are going to use the same the default parameters which we had. Yeah, cross validation, we will be using cross validation to shuffle to perform to get good combination of your hypertuning parameters. Okay, so though as of now it is not required in this scenario. Okay, so cross validation mainly to evaluate your model while building, while perform. See, with suppose with a different parameters, you might be building a different model, right? So cross validation will help you in getting the perfect combination. Okay, that's it. So LR dot fit of x underscore train comma y underscore train. Where is our model present in, guys? Remember this point. Our model will be present in the object which is being created for it. Okay, so our model is present in the object which is LR. Okay, now to get the prediction, I'm going to give the test data to it. I'm going to give the test data to my model. So I'll just use LR dot predict. We're having a method LR dot predict of. Here when you are predicting the output, we have to provide only test data, because obviously when you give inputs, the model will be predicting the output. Okay, so it is quite obvious we have to give only the test data to it. So LR dot predict of x underscore test. So I'm going to store it in a variable called y underscore pred. So print y underscore pred. See here, you got some outputs 0 1 0 1 something like that, but you are not quite sure whether it is a correct output or not. So how are you going to evaluate it? How are you going to check it initially? What are the actual outputs for this X test? What are the actual outputs for this X test? Values by the model. Okay, we are going to compare it with your Y test, Y underscore test. So you can see here, these are the respective, these are the actual outputs of your X test. These are the predicted outputs which are being predicted by your model. So you can see here there are some kind of wrong predictions. You can see here 1 1 1 1. So you can see here you have to get 1 here, but you got 0. Okay, sorry, you have to get a 0 here, but you got 1, which is a wrong prediction. Okay, so though it is quite hectic to constantly compare with all the values here, so what we can do is we can calculate the accuracy of your model based on what it has predicted using a metrics called accuracy score. One of the metrics which we can use is accuracy score. Okay, so one of the simple metrics. So from sklearn import accuracy score. So accuracy score is just so it's just a simple example. Suppose you have 100 questions. Okay, in that 100 questions, how many correct are there out of how many? Just like how you get marks in your exams. Okay, out of 100, how many are correct predictions? Okay, that means in the same way, out of total values, how many are correct predictions? Suppose if you see here, so total number of predictions will be 80, obviously, because we are having 80 train data, right? Out of 80, how many are correct predictions? The percentage of it is nothing but accuracy score. Okay, so this is one correct answer. Okay, so you can see this is one wrong answer. Okay, which is wrong answer, right? So like that, accuracy score is somewhat similar to that of correct prediction by total number of predictions. So for the accuracy score, we have to provide two values which are nothing but train prediction and your test data. So accuracy score of y underscore test comma y underscore pred. Okay, So here this is the test data which you're having, and this is the predicted data. So if you calculate the accuracy score, you can see here your model is 91% accurate. Okay, but this alone is not sufficient for you to confirm that your model is predicting good, or your model is performing better. This is not only one. There is not, this accuracy score will not a direct conclusion. There is one more metric called one more metric, confusion matrix. Okay, guys, there are a number of metrics for. I'm just showing you some of the evaluation metrics. So I'll just uh, confusion matrix. I'll explain you what is confusion matrix. No problem with that. So from confusion matrix. How to improve the accuracy of your model. See, as I've already mentioned, this is one algorithm. Okay, logistic regression is one classification algorithm. Okay, like that you are having a number of algorithms. Okay, so if you're not getting good accuracy, one of the simple one step is, if you're not getting good accuracy on one particular model, okay, we'll be going and we're going to check and perform it on other algorithms also. Okay, in those algorithms also, if you are not getting good accuracies, okay, one issue might be the data set. It is not having sufficient data set. Your model is not able to perform good because it is not provided with sufficient data set. Okay, or yeah, that's what, hyper tuning the parameters. Okay, hyper tuning the parameters will help you in increasing the accuracy of your model. Okay, even after hyper tuning also, if you're not getting good accuracy, then there's a problem with the data set. Okay, or there is no sufficient amount of data. Okay, yeah, so I'll just import the confusion matrix. So confusion matrix of y_test comma y_pred. Okay, so this also takes the same. Yeah, very good. Can a model be 100% accurate? Yeah, we can say it as 100% accurate, but it leads to one of the problems called overfitting. Okay, yeah. The model, if a model is 100% accurate, we can consider that as the model is overfitted. Okay, overfitting is nothing but your model is confined to only your training data. That means your model will be giving good predictions with the training data. That is nothing but your accuracy. Okay, but if you give a new data to your model, it will be giving wrong predictions. Okay, that is called overfitting. Overfitting is nothing but on training data you'll be getting good accuracy, but on the testing data you may not be getting good accuracy. Okay, with the new data you may not be getting good accuracy. That is called overfitting. Yeah, if you're having two CSV files, training test, okay, then it has already simplified, Sriram. We need not train and test. Okay, we can just apply directly your train data x and y parameters. We will be building the model. Okay, once you build the model, on the test data you have to perform the pre-processing. Okay, and that test data which are having the x and y parameters, that x parameter you give it here with the trained model, then you'll be getting the predictions. Okay, yeah. So confusion matrix. Now, so why the word says confusion matrix? In a bit of time you'll be getting to know why it is called confusion matrix. So how to see this confusion matrix? How we are going to find what do you call evaluate the confusion matrix, or how you're going to look into the confusion matrix. Okay, so we'll just stop it here and we'll have a quick click on this evaluation, how to evaluate your models, the same thing which you are discussing, but we can also a small presentation for you to help you in identifying the, help you in determining, understanding this confusion matrix and the accuracy score and all. Just a moment. Okay, so these are some of the evaluation metrics which are having accuracy score, confusion matrix, and AUC/RSC curves. So we'll be performing these three on our model. Okay, so first, as I've said, coming to the confusion matrix, coming to the accuracy score. So it is a ratio of number of correct predictions to the total number of input samples. So nothing but number of correct predictions by total number of predictions made. It's quite obvious, quite simple to understand. Accuracy score, which was already being performed on our model. Now coming to our confusion matrix, the word itself says confusion because people tend to confuse. Okay, so try to understand it. It's quite simple if you understand. So you're having two on the rows you're having actual class, and the column you're having predicted class. Just concentrate here first of all, so that it will be easier for you to understand the next. So predicted class, actual class. As I've said, you're going to evaluate your model based on the actual value and the predicted value. Okay, you can see here your model predicted it as your actual value to a particular record is 0. Your actual value for a particular record is S represents 0. For actual value, your output is actual for a single record. For a record, the actual value is 0. 0 should be the output, but the predicted value is, and the predicted value is also 0. So those many number of those, that count will be present here. I'm repeating it one more time. Actual value is 0. Predicted value is also 0, which is nothing but a correct prediction. Okay, so those are called true positives. Actual value is 0, predicted value is also 0, which is nothing but correct prediction, nothing but true positives. So suppose you're having, in the previous example, we had 80 records, right? In those 80 records, you should get some 40 zeros. Okay, so out of 40 zeros, you got some 38 as correct 38 as zeros, and the predicted values are also 38. The value will be 38 here. Okay, actual value is 0, predicted value is also 0, nothing but true positives. Actual value is 0, predicted value is 1. Actual value is 0, predicted value is 1, which is nothing but false negative and also a false prediction. The count will be increased here. The count will be increased for that particular category. Actual value is 1, but predicted value is 0, which is a false positive, which is a wrong prediction. The count will be incremented here. Actual value is 1, predicted value is also 1, true negative. It's a correct prediction. The count will be incremented here. So like that, how many records are coming into the respective categories, the count will be incremented. So here you can see there are, in this example, actual value is 0, predicted value also 0. Total number of those kind of records are 65. Actual value is 0, predicted value is 1, which is a wrong prediction, nothing but 3 wrong predictions. Actual value is 1, predicted value is 0, 8 wrong predictions. Okay, 8 wrong records like that, wrong predictions like that. Actual value is 1, predicted value is 1. 24 records are there. Okay, so this block and this block are the correct predictions. This block and this block are the wrong predictions. Okay, so you can see here the same thing is being given here. So in our data set also, we have to identify whether how many zeros are corrected properly, how many ones are predicted properly. Okay, that count can be evaluated using confusion matrix. Using this confusion matrix, we can perform one more evaluation called AUC ROC. Okay, there is one more evaluation called AUC ROC. We'll come to that. AUC ROC curves. Okay, so how this curve will be formed? So this curve will be formed using two parameters called TPR and FPR. TPR represents true positive rate, FPR represents false positive rate. True positive rate and false positive rate. Okay, so true positive rate, there is a formula. So how are you going to get this true positive rate and false positive rate? True positive rate and false positive rate can be obtained from the confusion matrix itself. Okay, so ROC curve represents receiver operating characteristics. AUC represents area under curve. So you can see here the area under this curve is nothing but AUC. Okay, ROC represents receiver operating characteristics. So this is the ideal curve which should be present. Okay, so we'll see that. So first we'll see how TPR and FPR are calculated. TPR is nothing but true positive rate. We can also call it as recall. We can also call it as sensitivity. TP by TP plus Fn. TP and what is this TP and TP plus Fn? TP is nothing but true positive. Remember from the confusion matrix. How many values you are having? That is nothing but TP. TP by TP plus Fn. Fn is nothing but false negative. Okay, which is nothing but TPR. If you see FPR, FPR is nothing but 1 minus specificity. Now what is specificity? Tn by Tn plus Fn. Tn is nothing but true negative by true negative plus false positive. So when you get these values and you plot a graph between that, if the curve is like this, then it is said to be an ideal curve. Then your model is an ideal model or a better performing model. Okay, the curve should be in such a way. Okay, the AUC value also is one of the parameters. The AUC value to confirm a model is performing better. Okay, the AUC value should be around greater than 0.7. Okay, area under curve should be greater than 0.7. We'll see for our model also. No worries with that. So just want to show you that TPR and FPR are the two parameters which are going to use to plot this ROC curve. Okay, so once this is the worst model which you might be getting. Okay, it will be purely inverted. Okay, if you see here the previous example, previous curve, this is the ideal curve. This is the worst model. Worst model in the sense AUC, area under curve, is 0. Okay, just like 90 degrees. Okay, this is the worst model, 0 accurate model. Okay, now 100 accurate model will be just inverted of it, exactly like this, which is nothing but an overfitted model. Okay, so these are the evaluations which are going to perform on our logistic regression. Okay, the model which is built on logistic regression. Okay, okay, so we'll just perform that on our model. Okay, I'll just open the program once again now. Okay, so you can see here now coming to the confusion matrix, the same thing which is being represented here. Actual values are 0, predicted values are 0. Like that we are having 56 records. Actual value is 0, predicted value is 1. Like that we are having 2 records. Actual value is 1, predicted value is 0. Like that we are having 5 records. Actual value is 1, predicted value is 1. Like that we are having 17 records. Okay, so total number of correct predictions, any one of you on the chats? Total number of correct predictions, how many correct predictions we are having? Anyone? 73. Very good. Okay, out of 80 records, yeah, 56 plus 17, out of 80 records, 73 are correct predictions. Obviously if 73 are correct, out of 80, 7 are wrong predictions. So 5 and 5 plus 2, 7, which are nothing but wrong predictions. Now we'll just go and build this AUC curve. Okay, in just a couple of minutes we'll be able to complete that AUC. Okay, So for performing this AUC curve, as you all know, ROC curve, we require TPR and FPR. So we can get those values directly from a method. Excuse me. Import sklearn dot metrics as metrics. Import the package. So metrics dot ROC underscore curve. So here we have to provide with y test and y train, sorry, y pred. Okay, the return values of these are 3 parameters. One is FPR, TPR, a threshold. This is a return type. I mean return values out of this ROC curve. Okay, execute this one. So ROC underscore AUC equal to, so we'll be getting the AUC value also, area under curve, metrics dot AUC of FPR comma TPR. You have to provide that to get our AUC value. So you can see here, as I've said, if you have removed, our AUC should be greater than 0.7. We got something around 0.8. Okay, which is a good model. You just plot it with a small, a basic plot, PLT dot plot of FPR comma TPR. Okay, kind of a small enhancements. You can just add it as label. AUC equal to I want only till 2 decimal points, 0.2 F. Percentile ROC underscore AUC. Some color if you want, you can just add it. Color equal to red. Okay, so I'm just going to plot and PLT dot legend. This will give you the label which is there. Okay, so you can see the curve here, AUC value, which is nothing but I'm audible enough, Jagdish. Okay, so yeah, so 0.87, which is nothing but your area under curve. Okay, so as I've said, your AUC value should be greater than 0.7, and you can see the representation of your RSI curve also. It's quite similar to what we have seen in our slide. Okay, so this confines that our model is accurate. Okay, so these are some of the evaluation metrics which are available. Okay, which we can perform, which we can see whether a model is performing good or not. And some of you have asked regarding this label encoding also. Guys, label encoding is nothing but, here we have to just create an object for it. For the label encoder, we have to provide the categorical column. Okay, now if you have remembered, our categorical column is nothing but gender. Okay, the syntax for gender is that to get the gender is using ilog. We can use a df.ilog, or we can also use it in a simple way like a df of gender. I'll just write it in comments. We can also use it in like this for applying it on your label encoder, df of gender equal to lb dot fit underscore. Now you don't need to do it, I just want to show you that. Transform of, yeah, I'll come to that point, Sriram. Okay, the same thing, this step and this step both represents the same. But if you perform now, you will not be getting it because you are already encoded that, right? Okay, so you can just use this step also. Yeah. So what is the difference between label encoder and one hot encoder? So mainly, guys, one hot encoder is mainly used if you're having more than two categories, then we'll be using one hot encoder, which will provide you binary columns, binary outputs. If you're having three categories, you'll columns of binaries. To represent three categories, we'll be using three separate columns of binary values. Okay, what do you mean by deploying is a model is nothing but, see, in general terms, deploying a web application is nothing but deploying it for as a service or as a web application. Okay, at the end of the day, what are the model you're going to build, that will be integrated to a application in the backend. Okay, that is nothing but deployment, integrating into your actual live application. Okay, yeah, Z score, see, Z score is mainly used for outliers, for finding out outliers. After finding out outliers, obviously we're going to remove it. Okay, so once you Z score, as I've said, in according to industrial standards, Z score value, if a Z score value of a particular data point, see here, this is your data set, right? For each and every data point, you'll be getting Z score. Okay, so formula of Z score, if you just Google it, you can just find it. It uses standard deviation and mean of that respective column. Okay, so the respective value of that data point, the particular data point, if that value is greater than greater than 3 or minus 3, then that point is considered as an outlier. Okay, so Z scores will just calculate those points. Okay, our outliers both categorical and numeric. Also, we can just convert into numeric and we can perform Z score on it. Okay, so yes, hope it is all clear. You Mr. Ritesh, is it okay so that we can wind up?
Yeah, I think it's done, right? So model evaluation metrics are also completely explained. It's cool. So thank you, guys. So if you have any questions, you can put it on the chat. We'll be there for another 5-10 minutes to answer.
Yeah, Giridhar, since we got only two categories, we will be getting 0 or 1 from the label encoder. If you're having more than two categories, you'll be getting 0, 1, 2, 3 like that when you perform it on using label encoding. But when you perform on one hot encoding, you'll be getting binary columns. So the main reason for when to apply label encoding, when to apply one hot encoding. Okay. But to understand that, you have to understand ordinal variables and nominal variables. Okay. So if you're having ordinal variables, then we can apply label encoding. If you're having nominal, you have one hot encoding. Okay, that's one of the important things. Okay, in general, if you're having only two categories, then we can perform label encoding.
Okay, guys. If you have any questions, you can put another 5 minutes. Will be there, or you can always write to us. I'm just giving my email ID in the chat, right? I hope most of you has already have my email ID, but still, if you don't have, you can take that email ID and you can post your questions. Okay, and we will sync up again next Thursday 3 p.m. with third algorithm, right? So meanwhile, you please practice these two algorithms which you have discussed last week, linear regression and today logistic regression. Okay, so you will be getting a recording of this link in an hour's time. So I hope you all know the YouTube channel which I've been sharing the recordings. You can go through the same YouTube channel in 1 or 2 hours of time. You can find the link over there, right?